The Casimir effect is a fascinating quantum phenomenon where two uncharged parallel metal plates in a vacuum experience an attractive force. This force arises from quantum fluctuations in the vacuum, where empty space is not truly empty but filled with fleeting electromagnetic energy. The plates, by restricting these fluctuations, create an imbalance in energy that manifests as a measurable force. This defies classical intuition, as it generates a force without external energy sources, particles, or fields. Scientists have measured the Casimir force between metallic plates separated by nanometer-scale distances, confirming its reality through experiments. It's like standing in a room with music playing everywhere. If you add walls close together, some sounds are muffled between the walls, creating a subtle pressure pushing the walls closer. In the quantum world, a vacuum is not an empty void, but a dynamic space teeming with energy fluctuations. These fluctuations involve virtual photons, which appear and disappear continuously. Normally, this energy is uniform everywhere. However, placing two closely spaced plates in the vacuum disrupts this uniformity, as the plates only allow certain wavelengths of virtual photons to exist between them. This creates a difference in energy density between the space inside and outside the plates. Think of waves in a swimming pool. If you insert two barriers close together, only waves of certain sizes can fit between them, while all wave sizes remain possible outside the barriers. It's like restricting ripples on water by placing two floating boards close together. The area between the boards suppresses larger ripples, creating a difference in wave behavior. The difference in allowed quantum fluctuations inside and outside the plates creates a pressure imbalance. Outside the plates, a full range of quantum waves exerts pressure on the plates. Inside the plates, only specific wavelengths can exist, resulting in less pressure. If two metallic plates are brought close together in a vacuum, the force becomes measurable at distances of a few nanometers, confirming the predicted effects of quantum fluctuations. Imagine air pressure acting on two closely spaced boards. The air trapped between the boards is limited in movement, reducing its pressure compared to the outside air, which presses the boards together. The Casimir effect has been observed and measured with high precision in laboratory settings. Using tools like atomic force microscopy, AFM, and microelectromechanical systems, MEMS, researchers have demonstrated the predicted forces between metal surfaces. These experiments align with theoretical predictions and validate the quantum nature of vacuum energy. A famous experiment used a small metallic sphere and a flat plate, measuring the force between them as they approached nanometer-scale distances. It's like testing gravity with a small apple and the Earth, where the apple's motion confirms the invisible pull of gravity, but here, it's the quantum vacuum creating the force. The plates act as boundaries that enforce specific conditions on the electromagnetic field. These conditions determine which quantum fluctuations can exist between the plates. The suppression of certain modes between the plates leads to a net energy difference, resulting in a measurable force. This highlights the profound role of boundaries in shaping physical phenomena at quantum scales. In electronics, manipulating electromagnetic waves with materials like waveguides works on a similar principle. The structure controls which waves can propagate. It's like placing walls in a river to control the flow of water. The barriers change the behavior of the river, creating forces where none existed before. At very small scales, the Casimir force becomes significant, influencing the behavior of micro and nanoscale systems. In nanotechnology, these forces can cause mechanical parts to stick together, a phenomenon called stiction. In microelectromechanical systems, MEMS, Casimir forces can cause tiny components to adhere to one another, potentially disrupting their function. It's like static electricity pulling two pieces of paper together. In the nanoscale world, the Casimir force acts like an invisible glue. The Casimir effect also extends to interactions between atoms or molecules and surfaces, known as the Casimir-Polder effect. This effect describes how quantum fluctuations create forces between neutral atoms and nearby conductive or dielectric surfaces, playing a critical role in atomic-scale physics. The Casimir-Polder effect helps explain how atoms near surfaces experience attractive forces, influencing atomic traps and cooling mechanisms in quantum experiments. It's like a magnet's pull on a small piece of iron. There's no direct contact, but an instantaneous force affects the atom's position. While the Casimir effect confirms the reality of vacuum energy, its role in the universe raises profound questions. The measured vacuum energy from the Casimir effect is much smaller than the energy needed to explain cosmic phenomena like dark energy. Understanding how vacuum energy operates across different scales is a significant challenge in modern physics. Cosmologists speculate that the vacuum energy driving the universe's accelerated expansion may be related to, but vastly different from, the energy observed in the Casimir effect. Analogy: it's like finding a small spring in your house that can lift a paperclip, but wondering if the same principle could power a skyscraper elevator. Advances in nanotechnology and quantum physics may harness the Casimir effect for practical applications. Researchers are exploring ways to manipulate this force using engineered materials, exotic geometries, or temperature variations. Potential uses include nanoscale actuators, energy harvesting systems, and precision measurement tools. By tailoring the surface properties of materials, researchers aim to control the magnitude and direction of Casimir forces, enabling innovations in nanotechnology. Analogy: it's like learning to sail by harnessing and controlling the invisible power of the wind, except here, the wind comes from quantum fluctuations. The Casimir effect demonstrates that empty space is anything but empty. By placing two plates in a vacuum, we reveal the tangible effects of quantum fluctuations, creating a force that challenges our classical understanding of physics. This phenomenon bridges the microscopic quantum world with the macroscopic, offering insights into vacuum energy, potential applications in technology, and even the nature of the universe itself. Example: the Casimir effect serves as a stepping stone for exploring other quantum vacuum phenomena, such as Hawking radiation near black holes or the interplay of vacuum energy and gravity. Analogy: the Casimir effect is like discovering a hidden breeze in an otherwise still room, an invisible quantum-driven force shaping our understanding of reality.